Hey, this is Mr. Ainsworth, and we're going to get into a little discussion here about exponential functions and discussing their two basic types, the growth exponential and the decay exponential. We're going to take a look at functions in the form of a times b to the x power, where a is called the coefficient. So let's get used to our basic terminology here. B is the base. All right, and notice the variable now. X, it's in the exponent. These are a lot different than exponent here. These are a lot different than their linear functions, even the quadratics and the cubics and other polynomial functions, because the base was not in the exponent, X was not in the exponent, it was in the base. And this time though, our variable X here is in the exponent, which changes the behavior completely. These growth and decay functions have a lot of applications, and we're going to explore some of the applications of the exponential in this lesson here. But first, let's go ahead and just review the two basic types of exponential functions. All right, we're going to take a look at the first one here in example 1. We're going to take a look at where the coefficient a is 100. We're looking at the base here is 0.5. Now remember, 0.5 is the same thing as 1/2. Which is between 0 and 1. And we're going to take that to the x power here and take a look at our first type of function called the decay exponential, or the decreasing function. We're going to use our technology heavily in this example so that we can review the basic concept. All right, so the very first thing we're going to do is we're going to take out our TI-84s or any graphing calculator you have, and we're going to enter that function in as 100 times the quantity. Okay, you can enter in 0.5 or 1/2. It doesn't matter. We're going to raise that to the x power. Now, in this example here, because the numbers can get very large and very, very small, we're probably going to have to change the window setting on this. When x here is, let's say, -1, this is actually 2. 1/2 to the -1 is actually 2. 2 times 100 is 200. So my output, my range, is going to have to go all the way up to 2 or 3 or 400, depending on what x values I put in there. You can get really large really fast when x gets negative. So we're going to change this, we're going to change the y max to, let's say, 300. You'll see that, ooh, that's the scale. Let's clear that out. But I'm talking about the y max. All right, let's go back up here and let's change y minimum, or x minimum, to be about -2. Let's change x max to be 12. You know, we're probably not going to need it to 12, but let's just keep it there. Y minimum, -4, that's fine. These y values are not going to be negative, but let's just keep it there. Let's take a look at the graph so far. You can see how when x is negative right here, -2, we get a large y value, and it cruises down here. It's decreasing. As x gets bigger, y gets super small. All right, we can see that in the graph here and what it looks like, but we also can see it in the table too. Now everybody hit the second window for table set. We're going to start the table at -2. That was second window, which is table set. Started at -2. It's probably different on your calculator right now because someone else used it. Go down here to go down, set the tables, the change in the table at 1. That's basically your step, or how you're going from one x value to another. So -2, -1, 0, 1, 2, 3, 4. That's what this number means here. And so that when we look at the table, we can see the values. So go second graph, which accesses your table. When x is 2, y is 400. When x is 1, y is 200. When x is 0, as x values are increasing here, the y values are decreasing. And the reason why is because the base is less than 1. We're taking half as much as the previous value. Half of 400 is 200. Half of 200 is 100. Half of 100 is 50. Every time you're taking half of it, and that's what happens in exponentials here. All right, so let's take this table here and let's go ahead and write it down here in the form of a table here, and we can plot these values. We're going to have to obviously change the scale here on the x-axis or on the y-axis here, because you got to go up to 400. All right, so we'll do that. So let's set up our values here. -2, and then once again, just look at your calculator. Starts at 400, and we're taking half as much each time because the base is 1/2. All right, so -2 is 400. By the way, let's figure that out. Y equals 100 times 1/2 raised to the -2 power. What is that? Well, it's 100 times 1 divided by 2 squared. Excuse me, 2 to the -2. All right, 1 to the -2 power is 1. 2 to the -2 power, what's that? Well, we got to shift that first, right? So 2 to the -2 shifts up top, becoming 2 squared. But we know that's 4. 100 times 4, well, that's 400. All right, that's why the calculator is giving you a value of 400 here. So we got to go all the way up to 400. So 50, 100, 100, 200, 300, 400. We can do that. So we count by 50s. If this is 50, this is 100, 150, 200, 250, 300, 350, 400. We can graph that. We're going to keep the x-axis with a scale 1. We don't have to have the same scale on both axes here. All right, keep that in mind. So my first point, if I was going to be plotting it, it would be right here, left 2 up 400. All right, and we can graph that function from there. Now, with a base of 1/2, the next y value is going to be half as much. That's why the y value for x equals -1, the y value is only 200, because half of 400 is 200. Half of 200 is 100, and so on. So for -1 here, we get 200. Again, divide by 2 here because the base is 1/2. At x equals 0, we have half of 200 or 100. At x equals 1, we have half of 100, which is 50. At x equals 2, half of that is 25. And then at x equals 3, we got half of 5, which is 2.5 or 2.5. Look at your calculator here. Well, I'm sorry. I didn't say that correctly. Let me fix that here. Half of 50 is 25. Half of 25 is 12.5. Okay, at x equals 4, it's half of that. Half of 12 is 6, and half of a half is a fourth. So this should be 6.25. Let's check the table here. Notice the 6.25. If you want to see more values, no big deal. Just use your calculator. Just scroll down, and you can get some more values. 5, 3.125. 5, 3.125. Use your technology. Go ahead and graph. So let's do this in red here so you can see this easily here. -1, 200 is here. Let me see, 0, 100. There's your y-intercept right there. Y-intercept. All right. 1, 50. It's right here. 2, 25. It's right here. 3, 12 1/4. You keep taking half. And so it's asymptotic to the x-axis here. This y-axis and this x-axis. So when we graph this function, it's decreasing very, very quickly because we're taking half each time. That's what happens when you have a base of 1/2. For every increment of 1 and the x value here, all right, you're taking half of as much as the y values. So once again, divide by 2. Divide by 2. That's what a base of 1/2 does. Divide by 2. Divide by 2, and so on. Divide by 2. And you can see that it's a decreasing, like, or what's called a decay function. So such a situation is called a exponential decay function. So let's write that down. Exponential decay. Once again, I'm just reviewing the basic concepts here. But I'm using a lot of technology here instead of doing everything by hand. Now, when you change the base to be bigger than 1, look at this. When the base is bigger than 1, like it is right here, b is 1.5, and where a is 1, you get what's called a growth function or an increasing function. So let's go ahead and let's change, oops, come on. Let's change the function in our calculator, and let's take a look at this one here. Once again, we'll change the scale and be able to graph all our points. So for this one here, let's go into y equals. Let's change this here. And let's change it to 1.5 to the power of x. Okay, and you know what? Let's clear this out. Let's put it in quantity here. Quantity of 1.5 to the x power. Okay, so you're taking 3/2, so 1.5, raise it to the power of x, and let's see what happens. Okay, things like this grow pretty darn quickly. So let's see the graph here first. I'm going to have to change the window here. Let's change it from -2 to 12. That's good. let's go ahead and change the max value to, let's see here. Let's see if 1,000 is going to be big enough. Let's test this out. Not very big at all. Because when you take 3 halves and when you take it to the 12th power, you get super big numbers. So we're going to have to change this Y max to something big. Let's change it to 10,000. There we go. Let's graph it now. Let's see if we can graph that better here. What's wrong here? Let me pause the video here and check something. Okay, we're just checking my calculator to make sure everything was okay, and it wasn't the calculator, it was me actually. I was thinking of something else here. The base is only 1.5, not 2. I was thinking for some reason it was a doubling sequence, and it's only 1.5 to the x power, so we don't have to have a big, huge y value here in order to see the graph, because we're going to take a look at the table right now. Go ahead and hit second graph, which is your table, and notice the y values here. They're not that huge here because it's not the doubling or tripling sequence or powers of 2 or 3. Notice when x is 12, y is only 129. So if we set our y max to around 100, we should be able to see most of these values here. So go back to your window, go down to your x max, y max, and set it equal to 100 so that when we graph it, we can be able to see all these values. Okay? So hit graph, and you can see it's a growth function. As x increases, so does y. It's growing here as x grows. Let's go ahead and plot some values. Let's get the table values first by going second graph so we can see the table. Now we want to start the table at -2. So go second window, which is your table set. Change it to -2. Set your delta table to be 1, which means we count by ones. Go ahead and now hit second graph, and you can see how your table starts at -2. All right, so when x is -2, we get 0.44 roughly. Let's go ahead and write that down. So -2, 0.44 for y value is about a little bit, almost a half. All right, when x is -1, we get 0.66, -1, 0.66. Again, just take your values, 0, 1, and then 1 and 1.5. 0, 1, 1, 1.5. That should make sense. 1.5 to the first power gives you 1.5. And when x is 2, you get 2 1/4. 3, 4, 5, 6, 7. So let's get some more values here. Scroll down just a little bit. All right, so when x is 3, we get 3.375. It's growing, but not as fast as the doubling sequence, as we'll see, or the powers of 3 too. We'll see that in the next part of the lesson here. When x is 4, we got 5.06. Yeah, there you go, 5.06, 5.06. When x is 5, it's 7.59. So 7.59, we're going to have to estimate these. And then 6, we've got 11.39. And then when x is 7, we have 17, roughly 0.009. So 17.09. I'm going to go one more here for 8. Let's scroll down. There we go. 8 is about 25.63. So 25.63. So things are increasing here. So as x gets bigger, y gets bigger. On the previous one, when x got bigger here, on the values are obviously getting bigger, the y values are decreasing, okay, by a half. That's a decay function. But for increasing or growth functions, both increase together. All right, that's what makes them behave so differently. So when we have for -2, let me see, we have to plot it all the way to, let me see, 2, 4, 6, 8. We got to go all the way up to 25. So I can't count by ones. So let's count by twos. 2, 4, 4, 6, 8, 10, 12, 14, 16. All right, we got 20 here, 24, and then 28. We should be able to plot all of these. And 2 here, 4, 6, 8, and over here is -2. So what you have to do is you have to look at your biggest y value and make sure you adjust the scale appropriately so you can sketch this function. Okay, so let's go ahead and do that. We got -2, basically a half. So left 2 up a half. See, that's 2 and that's 1, so it's right about there. All right, not very much, never very high at all. Left 1 and up a little bit more than half, so right about here again. 0, 1 is right here. It's the y-intercept. 1, 1.5 is right about there. 2, 2 1/4, right about there. You have to estimate, of course. 3, 3.3, so 3, 3.3, roughly about right there, maybe. 4, 5, so 4, 5, right about there. Again, this is 6, and so 5 is right in the middle. All right, obviously 5 is between 4 and 6. 6, 11, basically, a little bit more 11, so up. So 8, this is 10, 11 is right in the middle. So you have to estimate right about there. 7, 17, so 7, 17, right about there. And 8, 25, right about there. So you can see how it's asymptotic to the x-axis. No. And it's a growth function, okay? As x increases, so does y. All right? They increase together. All right, so this situation is called an exponential growth function. So let's write that down. Exponential growth. All right, the values, the y values get bigger as x gets bigger. Okay? All right, that's an example of a growth function or an increasing function. Notice they look totally different, okay? The difference between a decay function and a growth function. Now, how they're applied, well, that's what we need to talk about. So let's take a look at our first example here. Go ahead and turn the page. And check this out. Many real-world phenomena can be modeled by functions that describe how things grow or decay, as time passes. Examples of such phenomena, things that happen in nature, include the studies of populations, bacteria, AIDS virus, radioactive substances, electricity, temperatures, credit card payments, just to mention a few of them. Okay? Any quantity that grows or decays by a fixed percent at regular intervals is said to be possess exponential growth or exponential decay. Now, one situation that can be applied to either growth or decay situations is a financial situation dealing with how money increases or decreases over a period of time. Now, any growth function, and this is seen in the financial world all the time, can be expressed as a future amount here. Let's take a look at the growth first. A future amount is equal to the initial amount, okay, times the quantity 1 plus r, where r is the growth or decay rate. In this case, is the growth rate, raised to some time period t. All right, where t is sometimes measured in years or some period of time. So for a growth function, it's going to be 1 plus r. For decay, it's going to be 1 minus r in the same format. Now, in respect to money, things usually grow over a period of time, especially if you put them into your savings account or a checking account that has some interest rate, or if you invest it in some type of bank account that has an interest rate, your money increases over time. So let's read this here. The amount of money in an account after t years, all right, A of f. Okay, this is the future amount here, as I said up here, with the initial starting amount A of I dollars, earning at an annual interest rate R, is left untouched for t years. Okay, now we're in years, and it can be calculated by the growth function above, where A of I is the initial amount, R is your interest rate as a decimal, and t is the number of years. Find the bank account balance, okay, to the nearest dollar. Okay, find the bank account balance. That's the future amount right here. That's the future amount. All right, if the account starts at $100, that's the initial amount. Initial, starting, okay. That has an annual rate of 4%. And if it's left in there for t years. So t is equal to 12 here. All right, so t is equal to 12 years. R is equal to 4%. as we know, that's 4/100ths, or 0.04 is a decimal. All right, so how much money do you have after 12 years if you just let it sit and gain interest? All right, let's take a look at that. Okay, so here we go. Let's substitute our values in. We know we start off with $100, so we're going to put $100 into the account. All right, we're going to add 1 plus r, but r is a decimal, it's 0.04, to the t power. Now, what's t though? Well, let's put in 12, because guess what? T is 12 in this case. So this simplifies to 100 times the quantity, 1.04 raised to the 12th power. Now, remember, when the base is bigger than 1, it's a growth function. Let's write that down. So just a little note here. The base, all right, is greater than 1, so it's a growth function. Your money grows over time, guys, when you put it into the bank account. All right? So it's a growth function. The question is, what is this? You know, what's 1.04 times itself 12 times and then times 100? Well, let's figure this out. With a calculator, it's simple. Okay? So hit second mode, which is quitting out to your home screen. Let's enter in 100, all right, times the quantity, 1.04. And let's raise it to the 12th power because we're going to let it ride for 12 years. All right. After 12 years, we have $160 and roughly 10 cents. So $160.10. All right. After 12 years. After 12 years. So you start off with, this is the starting amount. You start off with 100. And then after 12 years, it gets to 160, which doesn't sound like very much. However, if you keep on adding money to it, it grows even faster. And that's what the whole idea of savings is all about. Put money in there each month, and you're going to have a whole lot more at the end of 12 years if you keep on doing that every month. Now, we're going to examine all kinds of growth and decay functions, and we're going to approach each one in a step process, three-step process here. We're going to build a chart and examine data. We're going to build a chart of data here. We're going to write, this is step 1. Step 2, we're going to write an equation. In step 3, we're going to prepare a scatter plot and answer some following questions here when we're taking a look at either a growth exponential or a decay exponential in real terms. Okay, so get ready. Why don't you go ahead and turn the page, and we'll take a look at our first application where you see a growth exponential in real life. Okay, and I'll see you in my next video on that.